So the second half of 6.5's video is just Simpson's rule, and we'll see the error bound for Simpson's rule at the same time. And also we'll find an inverse problem, which is a more practical question actually, of calculating the number of rectangles in if we want to bound our error by a certain amount. So we'll see that as a final example in these notes and in this video. So Simpson's rule to approximate our standard integral from a to b of f of x dx is given by the following. It's labeled s sub n. It's going to be the approximate value of that definite integral. And it's delta x over 3 is our formula times all the quantity in this brackets. So that's f of x naught plus 4 f of x1 plus 2 f of x2 plus 4 f of x3. So you'll notice that 4's and 2's alternate. One nice way to remember the formula is that the first and last have coefficients of 1. So f of x naught and f of xn have a coefficient of 1 per the formula. And all the odd coefficients have a factor of 4, while the even coefficients will have a factor of 2. So what we need is to choose n to be even, just thanks to the formation of this the structure of this formula. I won't work for an odd n. So if you were considering n equals 7, then you probably want to just bump it up to n equals 8 if you're going to make a decision. So you just have to remember that it has to be an even number for Simpson's rule. Delta x is the same as usual, b minus a over n. And yep, applying this formula is no different than the trapezoid or the midpoint rule, but we will see one example using it. So an error bound for Simpson's rule, we saw an error bound for midpoint and trapezoid rules as well in the previous video. So first we want to point out this fact that we now bound the fourth derivative of f by some value k on the interval a to b. So we want to find a bound for the fourth derivative of f along the interval a to b. And we use the same technique that we did previously, or set of techniques, looking at the graph, using a closed interval test, whatever calculus we can come up with to help find the maximum value or minimum value if it's negative of this fourth derivative. Only we're applying it to a fourth derivative instead of a second derivative. So you have to keep that straight, but that's really the only difference. The formula is slightly different. We have a fifth power here for the interval length, and we have 180 over n to the fourth. So some numbers change around a little bit, but for the most part, that structure is very similar to what we had for the error bound for the trapezoid rule and for the midpoint rule. One last thing I should say about Simpson's rule, it's that much more complicated. It's also that much more accurate, we notice. That's n to the fourth in the denominator down there versus n squared. So as n grows, n to the fourth is going to grow squarely in proportion to n squared. So it's going to grow quadratically compared to n squared, which is going to make this whole value that much smaller, that much faster, which is great because we want little error in our approximations. K bounded by the fourth derivative, that's a little bit more work. And this fifth power, that's going to kind of be sort of counterproductive to the work that's being done with our n to the fourth right there. But also this 180 does a pretty nice job of countering that out as well. So perhaps we might make this judgment. For shorter intervals, Simpson's rule is a very effective and accurate approximation for relatively few n compared to other rules like midpoint and trapezoid. But perhaps for longer intervals, we might want to resort to something like trapezoid or midpoint rule just because of that fifth power there. Last interesting fact about the Simpson's rule is whereas the midpoint rule is using the middle of a rectangle approximating area under a curve, and the trapezoid rule was using, well, a trapezoid standing up underneath the curve with its non-right angle edge sort of mimicking the slope of the curve along that interval. Simpson's rule is actually using sections of parabolas to cap the rectangles that are involved. So Simpson's rule is doing a parabolic arc from one subinterval endpoint to the next. And that starts to match the bend and the curve of the curve that we're trying to find the area underneath. And that's why it's that much more accurate. It's also why it's that much more complicated. So first example, use Simpson's rule with n equals 4 to approximate the integral from 0 to pi over 2 of cube root 1 plus cosine x dx. And again, it's worth pointing out, 1 plus cosine x, that has a pretty decent antiderivative, but as soon as we throw in a cube root in there, that's going to make it that much more of a mess. There's no outside sine function from this cube root, so there's not really a u substitution available to us. That's not 1 plus cosine squared x, or a quadratic form that we're used to from trig substitution, so that's not going to work. There's not really any multiples for integration by parts. So this probably, if it does have a closed form integral, it's at least difficult to get to. So it's a worthy function for worthy integral for using approximation. So using the formula for Simpson's rule, and noting that we do have n equals 4, which is even, so this is appropriate, we can do it. We write down delta x over 3. This is just the formula from the previous page, only now we've written it down for n equals 4. So remember, we start at 1 times f of x naught, and then we alternate 4s and 2s as our coefficients until we get to the very last one, and it has a 1 as a coefficient. So that's just a nice reminder. It's a good segue into using the Simpson's rule. And now we have n equals 4, so delta x is b minus a over n, which is 4. So we have pi over 2 minus 0 over 4. That's pi over 2 times 1/4, and that's pi over 8. Now, x0 is a, our leftmost endpoint. x4 should be b, which is pi over 2, our rightmost endpoint, but we add pi over 8 to each of these values as we step to the right, or we use our x sub I formulas from the previous pages in these notes. In doing so, we end up with pi over 8. Then pi over 8 plus pi over 8 is 2 pi over 8, which is pi over 4. And then add pi over 8 to pi over 4, that's pi over 8 plus 2 pi over 8. And we end up with 3 pi over 8. And lastly, 4 pi over 8 is pi over 2. So the details can be filled in by the reader, and I recommend that if you didn't see it. But the good news is we started at x naught as 0, x4 is pi over 2. Unless we made some mistakes in between that canceled each other out, which is unlikely, we've got everything set up correctly. Now the integral is approximately 1/3 delta x per this portion of the formula times f of x naught. So f of x naught is f of 0, but let's remember that's the cube root of 1 plus cosine of 0, and cosine of 0 is 1, and that's that component right there. Okay, and then similarly, f of pi over 8, that's 1 plus cosine pi over 8, all underneath cube root with the coefficient of 4. And then we proceed similarly for the rest of this. Pi over 4 can be simplified. Maybe we simplify that or not in terms of cosine. And then lastly, we end at cube root of 1 plus 0. This one is, again, a calculator would be very appropriate to find a decimal answer to this, but as these notes are usually done by hand, this is a sufficient place to stop. We note that we could use a half angle identity to evaluate 1 plus cosine pi over 8, but that's maybe a little bit above and beyond what we need to do for this. We did evaluate cosine of pi over 4 to be root 2 over 2, so we took it that much further. Stopping and how we simplify these is really either a matter of direction, or if you're undirected, it's just a matter of style. And that too, for if you're going to use a calculator. If you just plug this into the calculator, or you manipulate it a little bit to make it a little bit cleaner and easier to enter to a calculator. So that's it for Simpson's rule approximation. It's again just using the formula. Remember, you have an even number of ends, or rectangles, subintervals. So lastly, this is probably the hardest type of question from this section. And that's, how large should n be in order to guarantee that the Simpson's rule approximation to this integral, or integral, sorry, from 1 to 2 of 1 over x dx is accurate to within 0.00001. Okay, or 0.00001 is 10 to the negative 6. We write that down. Remember, that's true. You can check the decimals here. We moved to the right 6 places, 6 times, right? count those up, and that'll be 10 to the negative 6. So we need that accuracy, and what they're asking is this is our more practical question. We're out in the real world, and we want to know what the integral of 1 over x dx from 1 to 2 is. As an approximation, we need it to be accurate to within 0.00001. Right? Now I know we know the antiderivative of 1 over x, and that would be pretty easy to calculate, but assuming we don't know this function, at least we don't know its antiderivative, this is a practical setting. Also, we can consider we're going to plug this into a computer and have it integrate for us this definite integral. So the computer doesn't know calculus, but it does know arithmetic operations. So we need to see what arithmetic operations, well, we could feed it those arithmetic operations, but we need to see how many rectangles we need to break that interval from 1 to 2 into in order to guarantee that our accuracy is here. And the way to do that is to use our error bound formula. They ask us to do this for Simpson's rule, the midpoint rule, and the trapezoid rule. I'm going to do it for the trapezoid rule, just for the sake of brevity. Putting a bound on the fourth derivative of f really is not that difficult, but you have to take 4 derivatives, and it's that much more page to take up and write down. So I'll let the reader or the viewer complete that portion. So, it looks like I do this for the midpoint rule, I'm sorry, and then I'll have the trapezoid rules error bound for the reader to do, which are very similar because they both use the same kind of k, a bound on the second derivative. Simpson's rule, you have to find the fourth derivative and bound that. So write down what we have. We know that the midpoint rule has an error bound of this. So if we use n equals whatever it might be, which we don't know yet, then we know that this error is less than, the error of our approximation is always less than this thing highlighted on the right. So what we want is we want this value to be less than or equal to 10 to the negative 6, because then we know that our error is less than or equal to 10 to the negative 6 by transitivity of inequality. Okay, so b minus a, that's 2 minus 1. So we have that. K we don't have yet, and we don't know n. N is ultimately what we're going to solve. So the next thing we need to do is determine what k is. So to find k, we come off to the right. Remember that k is a bound on the absolute value of the second derivative of f on our interval from 1 to 2, our limits of integration. So a very similar situation to what we had before, only an easier function to take the derivative of. F of x equals 1 over x is x to the negative 1. So let's take a derivative. We get negative x to the negative 2. And another derivative is negative 2 times the negative 1 in front of x to get 2x to the negative 3. You might check those details on your own to make sure we've got the correct second derivative. We want to put a bound. We want to find what the maximum value of k is, which is, we want to bound g of x equals 2x to the negative 3 by k on the interval 1 to 2. So it's sometimes helpful and clearer to the reader to rename f double prime of x or after the fourth of x, or the fourth derivative of f of x, as some other function g of x. And that'll help us separate from the fact that we've taken some derivatives up here to get to where we are. And now we'll just look at this function sort of picked up by itself and say, we need to find the max or the min of this, if it's positive or negative. We need to find its max absolute value. And that kind of clears things up a little bit for us. So we'll use a first derivative test. G prime of x is equal to negative 6 times x to the negative 4th. Now, if we tried to set this equal to 0 for our first derivative test, right, we realize that no x value would cause that to be equal to 0. So there aren't any local min or local maxima on this. That's one nice thing, or at least if there is, we don't have that method of finding them. Remember that what we've done before is just graph this function. You could do that and confirm what we do in the next couple steps, but you should be able to do what follows here. You could graph this function and find the min or max. When we're at the first derivative of this function, now we're starting to assess whether or not it's increasing or decreasing and whether or not it has any local minima or local maxima. It looks like since this function is always negative from between 1 and 2, since it's always negative, g is decreasing. Remember that if g's derivative, g prime, is always negative, then g is a decreasing function. Okay, so we're able to conclude that g is decreasing on this interval from 1 to 2. Remember, this is back in applications of differentiation in Calc 1. You can have a look at the textbook if you need some reminders. So since g is decreasing from 1 to 2, it's highest on the left, and as we move further to the right, it's getting smaller and smaller values. We should also note that g of x is always positive, at least on 1 to 2 on this interval. If you don't plug in negative numbers, we won't get negative numbers. So it's decreasing and positive. So g of 1 is going to be our maximum value of this function. And g of 1 is, plugging in 1 to this function, we get 2 times 1 to the negative third, and that's 2. And just to check, we followed up and said, well, what does it look like at g of 2? It doesn't prove it, but it maybe makes us feel a little bit better that we chose probably the correct endpoint, if that was the solution to this. And we realized that g of 2 is 1/4. 1/4 is less than 2, so it wouldn't be a very good bound because 1/4 is not greater than this. So a lot of students ask at this point, well, can we just use the endpoints? Well, we could use the endpoints if the function's always decreasing. If it looks something like this, the endpoints are just fine from left to right on that curved segment. Now, or like this, increasing, something like that on this segment, in which case we take the right endpoint if it's positive, of course, if the whole curve is positive. And then, well, that's fine when the function's increasing or decreasing. We were lucky a couple times now that that's been the case. Now, a function that looks like this might be a little bit trickier. We could take a left endpoint or a right endpoint, but we'd be missing this local maximum. So that's why a first derivative test or a closed interval test is appropriate to really comprehensively know whether or not we have a max or a min. But graphing tools are pretty widely available, so graphs help out a lot too. So you just graph the function g that we have above, which is 2x to the negative 3, and see what it looks like from 1 to 2 and find its max value. It might at least give you a hint as to where to start looking. It might tell you, oh, it's at one of the endpoints. I can just plug in 1 to this function and go. So at any rate, we've got a bound on g, and g is f double prime of x. So we have a bound on the second derivative of f. So we choose k to be equal to 2, or set k equal to 2. Now we can come back, and this is the other harder part of this problem, and we write k equals 2 here. Notice that 2 minus 1 is 1. Cube that, we get 1. So we just have 2 in our numerator over 24n squared, and we need that to be less than or equal to 10 to the negative 6. Remember, that was our error tolerance that we were given, 0.00001. So we proceed this way. I'll write 10 to the negative 6 is 1 over 10 to the 6. That's a decent way to write that as two fractions. That way we can sort of manipulate things similarly and maybe do cleaner algebra. We notice that 2 and 24 have canceled out a common factor of 2, so we have 1 over 12 as our fraction on the left, and n squared is still in our denominator, of course. Now our next move, we're trying to solve for n. We want an n value that we want the least size n that will guarantee our error tolerance. So solving for n, we flip this fraction and this fraction on both sides. When we do so, remember that the inequality has to flip. So we flipped two fractions, we took multiplicative inverses, and we have to flip our inequality when that's the case. So now 12n squared, we're looking for 12n squared that's greater than or equal to 10 to the 6th. Divide both sides by 12 to further isolate n. We have n squared is greater than or equal to 10 to the 6th. In this step, what's happened is we've taken n to the 1/2 power. We've taken this side to the 1/2 power. So we raise each of these terms to the 1/2 power. Well, the 1/2 power of 10 to the 6 is 10 to the 6 times 1/2. So the exponents multiply in this case, and we'll have a 10 to the 3rd power down below. Now the 1/2 power of 12 is nothing more than just the square root of 12. And then of course, 1/2 power of n squared leaves us with just n, because 2 times 1/2 in the exponent will be a 1. So that's what happens in this step. We have a 1/2 power. And we now have n is greater than or equal to this term. And 10 cubed is actually 1,000. 1,000 over 2 is 500. And root 3 is just sitting there in the denominator. The calculator gives us this approximation. We don't need a lot of decimal points. We just need to know it's 288 point something, because then what we need to do is we'll choose n equals 289. We're not going to use 288.67 rectangles. Of course not. We're going to use a whole number of rectangles, and 289 is the next step up. We don't round because this is greater than 0.5. We round because we want to ensure that we have the least n that is large enough. We want n to still be sufficiently large that our error bound is still met, that we still have less error than 0.00001. And that, in fact, would do it. So that's it for the finding n for the trapezoid rule. Now, what I recommend to the reader, I'm sorry, this is not the trapezoid rule, this is the midpoint rule, as shown right here. But it's very similar to the trapezoid rule. In fact, you can recycle most of this work, or all of this work, in fact, and then you can start, the alterations you need to make to this formula for the trapezoid rule aren't much different, but start there, and you can calculate the n for the trapezoid rule to guarantee this error bound right here. So set it up so it looks like this, only using the trapezoid rules formula here. Now do something very similar for Simpson's rule as well. For Simpson's rule, remember that you're going to have a different error formula, slightly more, even more different than midpoint trapezoid is from the midpoint rule. And you're also going to have to calculate the bound on the fourth derivative. But you just keep churning out derivatives in this process. Call the fourth derivative of fg, have a look at a graph, or try to reproduce this method down below here as well. And that should work out quite nicely. So that's it for 6.5, approximate integration. It's a very powerful thing. It's very useful in practical application. And we'll see a little bit more of it and similar techniques to it as we progress in the course.